Okay, so I'll get to it. So welcome to this MaLGa seminar series. This is also part of the Elise Genova activities. So today is a pleasure to have Francesco Locatello. He somewhat, reminded us his trajectory in the last few years. He did a PhD in Zurich, and then spent a bunch of time in Google, both in Zurich and Amsterdam. His trajectory started with more kosher optimization stuff, the kind of stuff that Silvia Villa here likes, so greedy methods, conditional gradient, and so on. But in the last few years, he's been moving towards the problem of representation learning. Today is going to talk about the intersection between representation learning and causal learning, and somewhat the setup and the setting he has in mind is largely that of computer vision and situation where you need to have effective, transferable, and efficient representation for images, and more general, more specifically, maybe scenes. So it's a real pleasure to have Francesco. I forgot to say that he finished his PhD and is now at Amazon Research in Tübingen, which is very much geared towards, is a new lab, very much geared towards research. And well, as he was saying, and I guess they're looking for interaction. So hopefully this will be a chance to do it a bit with the center here. So I leave it to Francesco in a second. Just 2 words of Zoom logistics. First of all, if you have a camera and you want to leave it open for personal experience, this makes the life of the speaker slightly more lonely. You don't feel you cannot really feel the vibe, but at least you can see some faces. So please do if you want. And the format usually is that if you want to ask a question and make it a bit more interactive, is usually okay. So, and if you instead you want to collect, write question either on YouTube or on the chat, please do. Again, let's try to fight the Zoom format as much as we can. All right, Francesco, I leave it to you. It's a real pleasure to have you. I'm really curious to see what you talk about.
Thank you. Thank you very much for the invitation and the kind words. Yeah, so the title of my talk today is Towards Causal Representation Learning. This is meant to summarize basically what I've done in the last 2 years of my PhD, after I moved from more like theoretical optimization and Bayesian inference work to representation learning. This was actually supposed to be, this is actually a paper that I wrote. And when I decided I would speak about this topic here today, I was 100% sure the paper would be actually out. And of course, this didn't happen. So I'm sorry about that. I hope it's still going to be interesting, and then you'll be excited to look at the paper when it actually is released. So today I'm going to start introducing what is causality and why do we care about it. I'm a machine learning person, not a causality person, but I think causality is very exciting, and so I'm going to try to explain you why I care about it. And then I'm gonna talk more about deep learning things, in particular, disentangled representations. I'm gonna explain you what this problem is about, and how and why is it related to causality. We will see that the unsupervised learning of disentangled representations is rather challenging, and it has some critical problems. And we would have to go beyond the unsupervised learning to actually be able to solve them. We're going to see semi-supervised and weakly supervised approaches. Then I'm going to briefly talk about architectures and the importance of the representational format, and some hopefully inspiring conclusions on what I think is the way forward for bringing representation learning and causality closer together. So generalization is actually a very core concept in artificial intelligence. And this was recognized already in the very, very early days of AI. However, when we build and deploy a machine learning system, the generalization desiderata that we have actually have multiple facets. So we clearly want to be able to generalize one sample to the next in the IID setting, but also we want to be able to generalize across different settings. For example, if I train a neural network that is very good at recognizing chairs, then I would want it to be very good also if the chairs are presented with unusual backgrounds or unusual viewpoints. And finally, I would argue that generalization is also about being able to reuse and repurpose knowledge and skills. So that if I have a physical system, such as a robotic platform, and I train a model that learns to pick up the cube and then hit it with a third finger, then the knowledge of the environment that this model should have is the same that is needed to solve other tasks, such as, for example, inverting the order of a pile of cubes. And so ideally, we would want to learn this structure and share it across many different tasks. And the important remark here is that the performance of a learning algorithm inherently depends on the assumptions that you are willing to make. And the assumption that I decided to make in my PhD is that the world is structured. And now, if this statement is true, then it would be prudent to incorporate a corresponding structure in the solution of our learning algorithms. That's why in the first 2 years, I worked in convex optimization, in particular constraint optimization, when the structure is enforced as a constraint. And in the second half of the PhD, I worked on trying to discover this structure from data. And this is what I'm going to talk about today. And now the hope is that if we, incorporate this assumption, then we would facilitate learning. In particular, we will be able to reduce the number of examples that are needed to train a model, but also this would help with generalization, and in particular, stronger forms of generalization. And finally, this structure can be shared across many different tasks. And now, if we continue with this three-finger robot example, we can say now, if we have a task such as where will the cube land given some initial conditions, then we have many different ways of solving these tasks, and they're all equally valid. And here I want to focus on two extremes. On the one hand, we have physical modeling. So we know physics, we know differential equations, and if we know the initial conditions, we can pretty much compute where the cube is going to land exactly. In the other extreme, we have statistical learning, which is let's hit the cube 1,000,000 times and see what happens. Then we change the mass, we change other properties, and train a big model. And what I would argue is that both approaches are actually valid approaches to solve these questions, but maybe this is not the only question we care about on this particular system. And we don't even need to go to different tasks. But once I have a model answering this question, then I would like to also ask, well, how can I land the cube in some particular position that I want for some reason? Or what would happen if the cube was yellow, for example? And now these questions seem easy, but are actually pretty hard, because to really solve this type of problems, we need to go beyond statistical learning. And a nice example explaining the difference between statistical learning and causality, in particular interventional and counterfactual questions, comes from this paper that Matthews wrote in 2000, where he collected data about number of stork breeding pairs across Europe. He measured the human birth rate, and then he proved that storks actually deliver babies with statistical significance. So what does this tell us? Well, it tells us that if a new country arrives, then we likely can predict the human birth rate given the stork population. And this is quite reasonable to expect, because this sampling process should be roughly IID, or at least that's the hope. We are well within our assumptions, and so our model is expected to generalize. The second tier of this causality ladder are interventional questions. Interventional questions are like, if I want to improve the human natality rates, should I increase the number of storks? And of course, this type of questions is much harder to answer because it actually requires to have like an understanding of the mechanicistic processes that are behind the statistical associations. And finally, we have counterfactual questions, which is the hardest level of the causality ladder. And this is the hardest level because counterfactual questions are about things that actually didn't happen. So an example is, how would the natality rates be today if the Italian government had imported 10,000 storks in 1980? Of course, this is very hard from the machine learning perspective because we did not import storks in 1980, so we don't have an answer to this question. So the difference between statistics and causality is very well explained by Reichenbach in 1956. So he argues that if you have two observables, X and Y, and these two observables are statistically dependent, then there exists a variable Z, which could coincide with X or Y, that causally influences both and explains all the dependence in the sense of making them independent when conditioned on Z. So this means if we observe a correlation between the human birth rate and the number of storks, then either babies bring storks or storks bring babies, or there's some other variables such as economic development, which causally influences both. And from the machine learning perspective, we are interested in causal models because they offer a much richer description of reality compared to a statistical model. So one nice way to think about the difference is that if you have a physical system, a statistical model tells you something about one particular configuration of this physical system. And this is the configuration that you actually observe. While a causal model gives you a much more complete description of this physical system because it tells you about all the possible states this physical system could enter as a result of interventions. Of course, this is not as powerful as having like a full physical description of a system through like differential equations, for example. But the hope is that causal models could still be learned from data with some additional assumptions. And the reason why on the machine learning side, we are interested in causality is because we hope it's going to help in a variety of settings that nowadays corresponds to open questions in machine learning. And in particular, we've seen some preliminary but positive answers to this in the settings of semi-supervised learning, adversarial vulnerability, robustness and strong generalization in particular is something I particularly care about, but also common practices in deep learning, such as pre-training, data augmentation, and self-supervision, worm models and offline reinforcement learning in RL, and applications and multitask and continual learning. So this is great. On a very intuitive level, it's easy to be convinced that causality sounds like a useful concept for machine learning. However, there is a big elephant in the room here, which is causal variables. So causality starts from the premise that you are given descriptors for your physical system in the forms of causal variables. These causal variables could be observed or unobserved, but still they are part of your model. And so the language causality operates on is inherently different than the language we typically use when we do machine learning, and in particular deep learning. And so how can we, instead of relying on handcrafted causal variables, actually learn them? Because in representation learning, we don't have these causal variables, but we have images, for example. And here we have a very pretty picture of Switzerland. And the goal in representation learning is to learn a function that maps these observations into a low-dimensional vector representation. And now, an underlying assumption that we can make here is that the observations are not truly high-dimensional, but are the manifestation of a set of low-dimensional ground truth factors. Often these are called factors of variation in the disentanglement literature. And these ground truth factors would correspond to the causal variable we would like somehow to recover, because we hope that these causal variables would then have a certain set of properties that would be useful for downstream tasks, such as generalization, being maybe more robust to distribution shifts, and so on. So now I want to talk about disentangled representations and how this relates to causality, and how can we actually solve this inverse problem of recovering factors of variations from high dimensional observations. So this is my one slide connecting disentanglement and causality. So in causality, we have causal variables, Si, and we have the very famous causal graph that encodes the causal relation between these variables. And these causal relations can also be written as structural equations. So a variable Si is a function of its parents in the graph and some noise variables Ui. And the structural equation actually implies a causal factorization of the graph. So this set of random variables factorizes as P of Si given its parents. And now you can think of disentanglement as trying to recover these factors of variation under the assumptions that there is no confounder. So they're actually independent. So we have observations X that are a function of n independent variables, and we want to learn these variables. And if you don't want to assume that these variables are independent, this is actually equivalent to recovering the noise variables in a structural causal model. So a bit more pragmatically, this means that we want to align our representation with the ground truth factors of variation, so that when a factor of variation changes, then the representation changes accordingly in a single dimension. So in our paper, Challenging Common Assumptions in the Unsupervised Learning of Disentangled Representations, we first theoretically showed that for arbitrary data, this task is actually impossible. And the intuition is actually pretty simple. So here you can see 16 examples from the Cars3D dataset, which is one dataset which is commonly used in the disentanglement literature. And on the right-hand side, you see the representation that we would want to learn. This is a synthetic dataset which was generated with 3 factors of variation. And we want to learn this specific representation because, well, this is a synthetic dataset which was generated with these 3 factors of variation. However, we can construct a second set of ground truth factors of variation, which are fully entangled with the correct ones, but also give rise to the same observations. And now you can immediately appreciate where the problem is, because a representation learning algorithm that have only access to the observations have no way to distinguish from which narrative model these observations come from. Because from the observation perspective, these 2 generative models are actually identical. And so this is exactly how the theorem looks like. For any factorizing distribution over the ground truth factor Z, there exists a transformation f of Z such that the Jacobian is non-zero almost everywhere, meaning that Z and f of Z are completely entangled, because if I change Z in one dimension, then all dimensions of f of Z are going to change. But P of Z and P of f of Z have the same marginal distribution. And the intuition behind the proof is also very simple. Let's consider the example of ground truth factors that are just 2 scalars drawn from a normal distribution. And now the observations are a rotated version of the ground truth factors with some unknown rotation. So the rotation would be my generating function. And now the question is, can we obtain a disentangled representation? And this means, can we undo this rotation? Clearly, this is impossible because Gaussians are rotation invariant. So after observing the samples, I have no way of knowing, which were the correct axes before the rotation. So this is exactly how the proof works. We start from this factorizing distribution here on the top left, and then we map it to a Gaussian using the probability integral transform and applying the inverse Gaussian CDF. Then we apply a transformation there that preserves the distribution, the margin distribution, and then map it back to the original space. And now this whole chain of transformation have the properties that it preserves the marginal distribution, but also the Jacobian is non-zero almost everywhere, meaning that Z and f of Z are completely entangled. Now, this tells us that these entangled representations are non-identifiable from observational data. However, in this theorem, we make no assumption on what the data actually is. In particular, when we approach this problem from the deep learning side and the computer vision in particular, we work with images and we have very strong inductive biases on the architecture side. For example, we use convolutional networks, which tend to work really well on images. So, maybe inductive biases are sufficient to distinguish Z from f of Z. And the model just converges to the right set of ground truth factors. So to test this, we performed a large-scale experimental study trying to answer the question, can we learn these entangled representations without looking at the labels? Because we want to do this unsupervised. And to answer this question, we built a library to facilitate reproducible research on disentanglement. This library supports end-to-end training and evaluation of the prominent state-of-the-art approaches. We have automatic visualization, so all these pretty GIFs that you see in this talk are actually generated automatically for every model that you train. And we consider VAE-based methods. Now we have 14. Originally, in the first study, we had 6. These methods are all variants of the vanilla variational autoencoder. And all these methods basically enrich the VAE objective with a regularizer. And this regularizer is supposed to encourage disentangled representation through some suitable bias. Then at test time, we assume to have access to the ground truth factors, which is the case because we only consider synthetic data sets and compute some disentanglement metrics. And for the purpose of this talk, it's not particularly important to know what these methods do or what these metrics actually evaluate or are computed. So now I want to show just 2 results which relate to these 2 questions. We've seen that there are multiple methods. So the natural question is, which one is the best one? And the second question is, well, if I have a pool of trained models, how can I pick the best one? So here you can see the distribution of performance of these 6 methods that were trained on the CARS 3D dataset and evaluated with the factor VAE score, which is one of these disentanglement metrics. And now, as you can see, the performance of these methods is heavily overlapping, indicating that the choice of the loss function actually doesn't matter as much as the choice as the random seed and the hyperparameters. In fact, the objective function only explains about 37% of the score variance. So this first question actually doesn't matter that much, because if you can select a good model, any of these loss functions would do. So now how can we select this model? And here we tried many different things, and the TLDR is that nothing we tried really worked in a reliable way. But one result that to me really stood out is the following one. So here you see the rank correlation between the training metrics and the test disentanglement metrics. And as you can see, they are essentially uncorrelated, or at least there is no obvious trend that tells you, for example, well, having a very low reconstruction error is also an indicator that training was successful, and therefore the model is also going to be more disentangled. This does not happen. So the unsupervised training metrics actually do not seem useful for unsupervised model selection. And this question actually remains a key challenge. So this paper actually opened a bit of a crisis in the community. And in my perspective, this really raised two fundamental questions. The first one is regarding supervision. So we know that we need some supervision, both theoretically and empirically. Now the question is how much? Second question is about the usefulness of these representations. It seems like disentanglement is not a trivial task. So is it actually worth to learn this type of representation? And now to answer both of these questions, we need to go beyond unsupervised learning. And the first result that I want to show here is from this paper, disentangling factors of variation using few labels. Here, we ask a very simple question. What happens if we observe a few samples which have annotation from the ground truth factors? Let's say 100 or 1,000, which is less than 1% of the size of these data sets. Now, as soon as you have access to supervision, you have two options. You either train without supervision and use all the labels you have for validation, or you use the regular training validation split. And what we discovered in this paper is that both approaches actually seem to work. You can see two GIFs of the traversals on the bottom of the slides. But not only they work, but they are also surprisingly robust. So here you can see the rank correlation between the validation metrics computed with 100 examples and the test metrics that are computed with 10,000 examples. And this correlation is rather positive, indicating that we can indeed do model selection using our validation examples. And of course, like here, we need to be a bit skeptical because factors of variations are actually pretty hard to label, although we are only asking for 100 examples. So we also explored different types of imprecisions. For example, we can have coarse factors of variation where we just bin the factors into 5 categories. Some of these factors are discrete, so this binning doesn't even make sense, but we do it anyway. Or we have label noise. So 10% of the factors are actually completely random, or we have partial observations, only 2 factors are observed. And what we see here is that this correlation remains, which indicates that actually we don't really need that much supervision or like very precise supervision, because very little and very imprecise supervision actually seems to be enough. And of course, if you have more label data, you can just attach a supervised objective to your favorite unsupervised method, and this works even better, especially the more data you have, but this is pretty obvious. So maybe this crisis is actually an opportunity in disguise, because we've seen that little and imprecise supervision seem to be enough to actually identify these disentangled representations. And now in some applications, maybe you have a few labels, and so it actually makes sense to consider semi-supervised algorithms as opposed to fully unsupervised. But from the research side, this really raises the question, how far can we push it? How about we use 0 explicit labels, because that would be much more elegant, and only rely on weaker forms of supervision. And for this, we go back all the way to causality. And the critical assumptions that we add is what we call the sparse mechanism shifts assumption. So these assumptions say that small distribution changes tend to manifest themselves in a sparse or local way in the causal factorization. So they usually not affect all factors simultaneously. In a disentanglement setting, this looks as follows. We change the setup. We don't have IID samples from a generative model anymore, but we assume to collect pairs of non-IID examples. And across these pairs, several factors of variations are actually fixed. And of course, in practice, you do not want to assume which factors are fixed or how many. So the algorithm doesn't know anything about this. They only know that the change in the appropriate factorization should be sparse. And an example of this setting is you have a robotic platform. The robot is doing some task, and you have a camera, which is taking a video of the scene. And then you can automatically construct these pairs by taking nearby frames. And here we're operating under the assumption that two adjacent frames typically have mostly the same content. Maybe in pixel space, changes can be a bit denser. For example, when objects actually move, there are a lot of pixel change value. But in the appropriate factorization, almost everything remains the same. And from the theoretical perspective, it's quite intuitive why weak supervision is actually sufficient. So this is the slide I've shown earlier. And here I said, well, if you only have the observations, you cannot distinguish from which generative models the observations come from. However, if now I group the observations like this and tell you across these two images, only a sparse change happened, then clearly this second generative model could not have generated the observations. So to really give a formal statement, we need more assumptions. In particular, we assume that we actually know the number of fixed factors, and we also have a variability condition on this so that every factor can change essentially. We also assume that Z has a continuous distribution and that the generating function is a diffeomorphism. Then what we show is that if we do distribution matching and satisfy these constraints, then all plausible models have aggregated posteriors that are reparameterizations of the true aggregate posterior up to a coordinate-wise change of variable and index permutation. So every generative model with latent variable z hat, this latent variable z hat is a function of the original ground truth factor z, and the Jacobian of this function is actually diagonal now. Of course, the assumptions that we make in this theorem don't hold in practice at all. In particular, we don't know how many factors are shared. This number is not constant because it's unreasonable to assume this in practice. We have finite data sets. We have finite capacity for our models. We have a mix between continuous and discrete factors. And if we train VAEs, we also use the elbow for distribution matching. And so the distribution matching is actually approximate. But the good thing is that inspired by the proof technique, we can actually develop methods for which the training metrics actually correlate with disentanglement, meaning that now finally we are optimizing for the right thing, first of all. And second, after we train our model, we can do model selection just looking at the training metrics. For example, taking the model with the best reconstruction error or the best error. We typically use the reconstruction error. And on the left-hand side, you can see the traversals of the model achieving the best weakly supervised reconstruction error, which also achieves almost perfect disentanglement. So on the supervision side, we've seen that under some condition, we can actually recover the factors of variation with no labels. Of course, these conditions are rather strict, but in practice, at least the training metrics can correlate with disentanglement, meaning that at least we can do model selection. And now the second question is, should we do this at all? And here we consider three different tasks, and these tasks are extremely different. So one is abstract visual reasoning. So here we are given a set of panels in this grid, and one panel is missing. And these panels are related to each other by some high-level logical rule. And now the neural network needs to find the missing panel out of a set of potential answers, which are the 6 panels on the right-hand side. This is extremely hard for neural networks because you cannot solve this task just by looking at local features. You really need to reason about the similarities between these pictures in factors of variation. The second task we consider is strong generalization. So here, after training the representation, you're given a training set and a task. For example, you want to classify the shape of the object mounted on this robotic arm. But the training set is extremely biased. So all the objects are white. And in the test set, objects can take any color, and none of them is actually white. And the third task we consider is a fairness task. So here, the setting we assume is slightly different from what is typical in the fairness literature. So here we have independent factors of variations, one of which is the target variable, one of which is the sensitive variables. They get mixed into the observations with some unknown mixing function. And typically in fairness, the sensitive variable and the target variables are related to each other. And in our case, they're independent and they become conditionally dependent given the observations, of course. However, the other assumption that we make, which makes the problem much, much harder, is that we don't want to have any label for the sensitive variable. We only observe the target variable. We want to train a classifier which accurately predicts the target variable, but is also robust to changes in the sensitive variable. And this we measure with a notion of fairness, which is called demographic parity. The definition is on the top here. And you can interpret it as the probability of a classifier predicting a certain candidate should get a job is true, given that the gender of this candidate is male, then this probability should be the same if the gender was equal to female. So in this panel here, you can see the rank correlation between disentanglement and our weakly supervised reconstruction and the unfairness on the different data sets that we consider. Here, you can see the performance on this abstract visual reasoning task at different sample sizes. And here you can see the strong generalization performance. So what these three tasks have in common is that disentanglement is a useful property on all of them. However, these disentanglement metrics are a bit meaningless in this case because we don't want to assume to have access to the ground truth factors, otherwise we would have to compare also against supervised approaches. But now with weak supervision, we have our weakly supervised reconstruction that actually correlates with performance on this task. So this means that the model achieving good reconstruction, the representation that this model has learned will be useful for all of these tasks at the same time. So overall, this weakly supervised disentanglement has some recovery guarantees, and reconstruction loss identifies models that actually learn this sort of reusable abstractions we wanted to learn in the causal sense in a way. So the usefulness, we ticked it. We can identify representations that are useful for diverse tasks in terms of performance, strong generalization, and sample efficiency. This is what we've seen. So disentangled representations are an active and important research area, but the use of inductive biases and supervision needs to be much more explicit, because in the unsupervised setting, we've seen that there are fundamental challenges. And the type of supervision needs to be data and task dependent. And finally, one takeaway from these studies is that it's very important to have sound and reproducible experimental setups with several data sets, because it's very easy to draw spurious conclusions if you only look at a subset of these data sets. So are we done? I would argue that we are not done. And a clear example is in this slide. So I started talking about disentanglement, showing this very high dimensional and complicated picture. And then the data sets that I used were these like super simple 64 by 64 pictures with one object in the center. And here, the very important difference between these two pictures is not just the resolution or the lack of textures, but also the fact that in the data sets that we consider, there is only a single object, while in reality, we have multiple objects, and even worse, we have multiple instances of the same object. And this is a problem, because let's say we have this robotic platform, and we train one of the models I've just talked about using this weak supervision, right? Now, the hope is that this model actually learns something about the physics of this environment. But now, if I change the problem, and now I have 3 objects in the arena, then now my representation is either not disentangled anymore, or it can only store a disentangled representation for a single object. So the fundamental problem here is that I've been talking about disentanglement for so long now, but I'm still using a distributed representational format. And so this is one way to interpret slot attention. Slot attention is a differentiable interface, so it's a layer between distributed and set representations of task-dependent high-level variables. It's very similar to capsule nets, but the main difference is that capsules in capsule nets specialize to always bind to a particular class, while in our case, the slots can bind to any entity in the input scene. And this binding happens through an iterative and competitive attention procedure on top of a learned encoder. And this attention competitive procedure can be thought of as a meta-learned clustering. And now I'll show you why. So this is how slot attention works. It takes as input feature maps and position embedding. Then you have an iterative procedure. First, you initialize the slots by drawing from normal distributions with learn, mean, and standard deviation. And then you iterate, and you first compute the dot product between projection of the inputs and the slots. Then you take the softmax, as in regular attention, but now you normalize the softmax over the slots axis. Then you take a weighted mean instead of a weighted sum to compute the updates. And you update the slots using a gated recurrent unit. And now if you look at this pseudocode hard enough, you will realize that it's basically the same as soft k-means with some minor difference. So in soft k-means, you initialize the centroids. In this case, we call them slots. And then you have an iterative procedure. You compute the Euclidean distance between each point and the slots. You take the softmax for the soft assignment, and then you actually perform the update, which is the weighted mean of the inputs with the weight from the softmax. This is recomputing the centroids. And then you just replace the old value of the centroids with the new one. So slots in slot attention can be thought of having to compete for explaining parts of the input, very much like a clustering algorithms. In this case, it's meta-learned because, first of all, we meta-learn the objective function is not just the Euclidean distance, but we have these learned projections. And then we have this parameterized update with the GRU. So slot attention has two key properties. The first one is permutation invariance with respect to the input. So if I permute the input, the output of slot attention is the same. And this means that it's suitable for set-to-set processing. If I want to do grid to set, so distributed representation to set, then I need position embeddings. The second property is permutation equivariance with respect to the slots. So if I permute the slots, then the output order of the slots is the same, like it's permuted in the same way. And this is useful because slots really act as object files that learn a common representational format, and each slot can bind to any object in the input scene. So this is how you use it. You have a convolutional neural network. You place slot attention in the middle, and then whatever you do on top, you apply it with shared parameters across the slots. For example, if you want to do object discovery, you have a decoder applied on each of the slots, which will reconstruct one object at a time. Or if you want to do supervised learning, you apply an MLP head, and then you need to match the prediction with the ground truth labels using some matching algorithms. An important property here of slot attention is that the number of slots can be changed at any time, in particular at test times, because the number of objects we can represent is actually arbitrary. So it works fairly well. It's competitive with baselines. In particular, we compare against the deep subprediction network, which is a proper set representation. And this is already much better if you use an MLP as if it was a set method. So like you enforce an arbitrary ordering of the slot in the distributed representation, as you would do, for example, in disentanglement. And of course, there are tricks to make the method much better. This is not particularly exciting. What is exciting is that object masks, which are not supervised, actually emerge during training and segment the scene in a reasonable way, achieving actually a pretty decent ARI, which is a segmentation metric. And at test time, you can change the number of objects. And here it really means changing the architecture to increase the number of slots. And of course, the performance degrades because the problem is also harder, but it degrades gracefully. If you had a distributed representation, you would not be able to change the number of objects in this way. So I think these slot-based architectures are very promising for learning and reasoning about objects. And attention is an extremely powerful mechanism that can act as an interface between perception and abstract representations. And there are a bunch of limitations which would be very interesting to explore. For example, having hierarchy so that you can have still some degree of specialization, but in the same way that is in programming. So in programming, you have classes, and then you instantiate as many objects as you want from a given class. And now the second limitation is also that these variables are only task dependent in slot attention. And we don't really have strong biases from the data side that you would have, for example, if you consider like videos. So to conclude my talk, what I'm interested in is bringing representation learning and causality a bit closer together. And in my opinion, the fundamental limitation here is that these two fields talk a different language, because the dictionary in causality is the starting point, are these causal variables. And in representation learning, you work with images, for example. But the desiderata is to perform causal reasoning on learned representations. And here we can think of these images as being a partial view on the state of a physical system with some underlying causal structure. And now causal representation learning is about training a neural network that learns an appropriate descriptor for this physical system that support causal statements that are useful and relevant for a set of downstream tasks that we actually care about. Because it's very difficult to talk about causal graphs for images because there's no one true causal graph in nature. The granularity of the causality statements that you can make depends on what you care about. If I care about moving these objects, then the appropriate descriptors are likely the objects. If I care about how these objects are made, then I should probably look into the molecules and stuff like this. So the key question going forward now is, why do we need any of this? Because the skeptical listener would say, well, why can't we just train big networks? Because if structure, and in particular causal structure, was useful at all, a network could implicitly learn it in a distributed format if we have enough data and enough episodes. And the short answer is that it's unclear whether we need it or not. And GPT-3 is a great example for this. However, I would argue that generalization, and in general, the performance of a learning algorithm, is related to the assumptions that we make. And in deep learning, we make plenty of assumptions too, on the architecture, how we train the model, on which data we pre-train the model. And we need to talk about these assumptions explicitly so that we can selectively incorporate the ones that we truly want in the training framework. And here the example is the inductive biases in disentanglement that we're supposed to turn this problem from impossible to possible, and then in practice didn't really deliver on it. Thank you. I hope I'm
Thanks, Francesco.
not too over time.
No, you're good. Okay, so yeah, so I guess we have time for questions. So I mean, maybe I'll kick off while we see if somebody has any curiosity. So I guess some question that I had is, a while ago, I mean, there is this idea that, for example, when you talk about disentanglement and the different kind of variation, for example, you can try to make some strong assumption of the kind of variations you have to do. There are many different kinds, right? There could be geometric variations, viewpoints, and then there is the idea that you can take a group theoretic point of view where, in some sense, these changes are quite rigid, that they don't have a lot of degrees of freedom. But then if you start to talk about more substantial things, So people talk about, for example, of a small deformation, but if you start to allow deformations, then you can do all kinds of things, and then even like semantics can be seen as a sort of nuisance.
Yeah.
So I was wondering, I'm not an expert about the disentanglement, and I was wondering a bit in this landscape of potential changes you want to disentangle, how you can distinguish between what's like more rigid and is more flexible, and what is the semantics. In the end of the day, it seems to me that it's very much task-based. Depends on what you want to do. You will want to factor out something, and I don't quite see what is a general way to think about this and how it relates to what you were discussing.
Yeah, I think this is a great question, and this really highlights why unsupervised learning, I think, is not good for this, because if you don't really put any like constraints on what you want to model as factors of variation, is really hard to actually learn something meaningful, because like the only possible solution would be to learn the representation at the most fine-grained, like the most possible fine-grained representation you can get in terms of factors of variation, because yeah, you have no other information. So I think like in the weakly supervised case is where things actually get interesting, because what is a factor of variation is induced, of course, from the task if you have some sort of supervision, but also on how you construct these pairs, for example. So we said that factors of variations can change, are things that change sparsely. And so if we never see something changing across two frames, then this thing would not be a factor of variation. And this is, to me, very interesting, because it's somehow disaligned from what I think factors of variation should be, right? Like, for example, like object class should be a factor of variation, because why not? But this is also like pretty rare to, like you see a video of a ball rolling and then it suddenly turns into a car. So maybe this should not be a factor of variation. And I feel it's very exciting that factors of variation are actually data dependent, and they depend on which interventions you can perform, because this opens up a whole lot of possibilities for machine learning, in my opinion. For example, like to understand
then there seems to be
how, yeah.
As I was saying, then there is a trade-off between somewhat the universality of the representation and the task specificity, right?
Exactly. But there's no free lunch, right? So
yeah.
You need to pick. And we do this already in deep learning. Like data augmentation is basically doing this, right? When you have an image and you algorithmically generate an intervened version of this image, and then you ask your representation to be invariant to this transformation, you're basically asking, you're introducing, a style variable, and then you're basically asking your representation to ignore it.
Yes. Yeah, absolutely.
So maybe while we are waiting, there is a question on YouTube by Bashir Sadeghi, which says, based on your representation, can we say anything about representation dimensionality?
Okay, so I think if you have infinite data, then you could, in principle, like, learn what's the implicit dimensionality of the manifold this data lives on. More pragmatically, in our experiments, we fix it to a number. And this is a hyperparameter, and we actually didn't even make a sweep on it. We just kept it fixed to keep the computational budget in check.
Okay. Other questions? Otherwise, yes, we can thank Francesco. This is the usual Zoom format. So thanks a lot. It was super interesting and super stimulating. So again, we'll probably get in touch so that we can have a bit more of a private conversation.
That'd be great.
Thanks a lot for today. We hope to have you here in person very soon.
Thank you. Thank you very much. Have a good day.
Okay.
Thank you.